Good afternoon, ladies and gentlemen, and welcome to the Geological Society of London, and this, the fourth of our public lectures. Thank you very, very much for coming here today. As some of you will be aware, yesterday and the day before in this very lecture theatre, we ran a conference on lithium. So actually, it's absolutely brilliant that we've got Kate here today to continue along the theme of really exciting elements, etc. So firstly, before I give Kate a proper introduction, health and safety, as far as I'm aware, the alarm is not supposed to sound today, so I seriously advise all of us that if we do hear the delightful tones of the fire alarm, we might like to leave. There is a fire exit here to the front, which will take you out into the main courtyard of Burlington House. So you can go that way, or alternatively, you can go out any of the back doors and out onto Piccadilly. Just be very, very careful of fire engines as they come screeching down the road, and make your way round into the Burlington House courtyard as well, because then we'll make sure that you're all okay. However, hopefully, there won't be a fire alarm. Also, if anybody feels at all unwell, please do let us know and we will look after you. We won't let you sit and suffer. Finally, if any of you have one of these, or a smartphone, or a less smart phone, etc., please can you make sure that it is turned off? Alternatively, the deal is, if it does ring, you can answer it, but you have to put it on speakerphone so we can all listen into your conversation. Is that okay? Yeah? Okay, so please switch your mobile phones off. So today's lecture, which I'm really excited about, is entitled The Role of the Geologist in Securing Supplies of Critical Raw Materials. And it is my pleasure to introduce our speaker today, Dr. Kathryn Moore of Camborne School of Mines. The raw materials supply chain does not respond rapidly enough to demand or supply shocks caused by price fluctuations and shortages, or causing price fluctuations and shortages. Assessments of security of supply have identified those minerals and metals that are most critically subject to those demand-supply imbalances, typically those used in new and advanced technologies, produced in small amounts, often from a small number of mines. Big companies are responding to the exhaustion of large deposits of high-grade base and precious metal ores by using innovative methods to increase throughput and process low-grade ore, increasing the mine's useful lives and investment security. Smaller operators, however, target small and often complex ore deposits for those critical metals, but may struggle to secure the investment and also may struggle to sell those projects on to the mining companies with large overheads. What we need is an approach that builds secure, long and short-term supply and increases the competitiveness of small ore deposits for the creation of a larger number of mines with wider global distribution. Kate Moore gained her degree in geology at the University of Edinburgh. She went on and did a PhD at Bristol, and then went on and did a diploma in archaeology in Galway, which is really exciting. She led the Magmatic Studies group at Galway from 1999 until moving to Camborne in 2012. As a lecturer in critical and green technology metals, linked to the BGS. She is expert council leader in the high-tech ALCARB, i.e. new geomodels to explore deeper for high-technology critical raw materials in alkaline rocks and Carbonatites, and is the project lead for IMPACT, spelt amazingly with a special @ sign in the middle, which is the integrated modular plant and containerized tools for selective low-impact mining of small, high-grade deposits. Ladies and gentlemen, please put your hands together for Kate Moore.
So, firstly, thank you very much for inviting me here today. It's an absolute pleasure to see so many people interested in this subject. What I want to discuss today is really a rather personal view of the critical metals situation, because obviously we have all a different viewpoint on something that is potentially quite specific, because there is an enormous number of raw materials that we use, and each industry uses them in a different way. And what we even perceive as criticality depends on where we're coming from. Is it an academic perspective? Is it a manufacturing perspective? Or is it a political perspective? And so the view that I would like to describe to you today is basically a description of the journey that I've been through myself, translating my work as an igneous petrologist into that of a lecturer in critical and green technology metals. And my remit was really to find ways to secure supplies of those metals. And so what I have found is that where I have come to now is not where I thought I would go when I started this journey. So, a little bit of an introduction first of all. What am I going to talk about? I'm going to describe some of the definitions of criticality, what they mean to different people, where are the critical pinch points in the system. And we need to think about that all the way from the start of exploration and extraction, all the way through to the end of recycling, because the whole system is connected. And of course, as geologists, we are chasing the commodities that technology designers are requiring us to find. And so to know what the next big thing in technological development is, does have a role to play in where we go to as geologists. So some of the case studies that I will use today describe what we would normally think of as pure geological research relating to how deposits form and how we find them. But then thinking more about once we've found them, how do they vary from the big bulk metal ore deposits that we're used to thinking about? And how does that difference actually influence the whole of the system, from extraction to minerals processing and recycling? And then thinking about the engineering, the mining technologies that it takes to really make a difference. And what's really, really important currently is the social sustainability of mining. And that's really, I think, one of the greatest challenges that's facing the sector at the present time. And what we need to think about is what kind of shift do we need in exploration and mining practice? And how do we translate this from a vision into a reality? So that's quite a lot to get through in an hour. So hopefully we do manage to get through all of it. But this is hopefully a graph that some of you may have seen already. So this is the very simple graph that actually depicts an enormous amount of work, where we've got a supply risk up the y-axis and economic importance on the x-axis. And basically, there are a lot of variables that are considered by a consortium of researchers, Deloitte Consulting, the British Geological Survey and others, on a fairly regular basis every few years. So the last one was published last year. Before that, it was 2013. And what I've got here, in 2017, more than 60 raw materials were assessed. In 2013, it was 54. In 2013, 23 materials were identified as critical raw materials. Now that's gone up to more than 25. And so what's happening is, as this research field grows, the assessments expand, and we realise the situation is potentially more challenging than we originally considered. So what is it? Essentially, a critical raw material is a raw material that is fundamentally important to new technological manufacturing. The green energies are a classic example. The iPhones, the tablets are another. The electrical vehicles are another. So these are really, really important. And that's what's on the x-axis there. The y-axis is how easy it's going to be for the manufacturing companies to actually get their hands on those materials. And if a manufacturing company can find a supply from one mine, how likely is it that that mine is going to be able to persist in supplying that particular commodity? And so those materials that are at greatest risk and are most important to the new technological manufacturing fall in this top right box here. And essentially this particular plot is contracted as a part of a report by the European Commission, but the United States Geological Survey does its own. There's a new one out by the USGS for critical raw materials in the United States. And obviously the British Geological Survey is at the forefront of providing mineral statistics for Britain and the European Union. But there's this other caveat down here. Underneath the website, you can actually freely download the entire report and all the figures that are in it. But it says, all raw materials, even when not critical, are important for the EU economy. And that's something I noted with interest, and I came back to time and again, is that there are a lot of lessons to be learnt from the supply of all raw materials, and there's a lot to be considered when we think about critical raw materials supply in a larger context. So what is the biggest problem with the supply risk? Well, the problem is that these critical raw materials, you can imagine, I'm imagining a lot of you already know that in your mobile phone, you have either, well, anywhere between 1/2 and 2/3 of the elements in the periodic table are used in the manufacture of that mobile phone. And it's not a very big thing. So those elements are being used in very small quantities. So if you don't use a lot of them in your manufacturing, then there isn't a huge tonnage of them required each year. And so what that means is that one big mine can actually supply the world of a particular commodity. A classic example down here, there's a mine over here which produces niobium, the Arashar mine. Over 90% of the world's niobium comes from that one mine. What would happen if, for some reason, that mine had to shut down? Okay? And these things do happen. So we have blips. And what we can see here, this particular map, is showing countries, China is a great example here, which actually produces up to, well, 90% of antimony and more than, well, 40% of a lot of critical raw materials. And very specifically, this is supplied to the European Union. So here we are in the European Union with a lot of high-spec technological manufacturing, and, yep, France produces quite a bit of hafnium. We've now actually got a lovely mine down here in Devon producing quite a lot of nice tungsten. So we are starting to increase European production, but we are still, as a manufacturing community, utterly dependent on mines from outside Europe. Okay, so the obvious next question is, if we're really great at technological manufacturing, and we're also getting to be really, really good at recycling, can we not just recycle all the critical raw materials and put them back into circulation? And the answer is not really. So this graph here is showing an increase in consumption over time. And what we see is that a lot of the modern technologies lock those elements into what we're now describing as the technosphere. So if the wind turbines have a life expectancy of several decades, then the critical raw materials that are put into those motors in wind turbines are not going to be released in any meaningful time frame. And if we use the mobile phone technology again, we can consider that those of us who upgrade mobile phones regularly, what do we do with our old mobile phone? How many people have a few deposited in a drawer somewhere in their home? And so the collection of these technologies is the first big stumbling block to recycling. The second big stumbling block is that a lot of these elements are used for alloying or doping, so that the screen on the surface of your tablet or your mobile phone will contain trace amounts of things like indium that is very, very difficult to unlock from those alloys. And so that means the only way recycling is going to make a really big dent is when we no longer increase our consumption and when we can recycle 100% of the elements in the technologies. Until that happens, we will need to increase our extraction of raw materials from geological deposits. And the other one that often gets cited is substitution. If we have an increasing demand and we find that we can substitute one mineral for another. So if tungsten is in short supply for alloying for steel, we could put in some vanadium. And that would decrease the amount of tungsten that we need. The problem with that is that decreasing the demand for a critical raw material actually means that we need fewer mines and we can concentrate supply further, and we may actually increase risk in the system again. So the problem is a multifaceted one. And we can also now think about that bigger context. So it's a bit of a sketch graph there. But what we have with big bulk raw materials, copper, zinc, lead, iron, is that if we have an increase in demand and output is fairly static, then the price increases. And after the price increases, investors take note and they start putting money in, and there's a bit of a time lag, but investment in exploration goes up, and then we find more deposits, and after a while, some of that investment will translate into new supply. So there's a time lag, but generally speaking, exploration and supply catches up with demand. But that's for big bulk materials that are used in vast quantities, where big mines already exist and can expand to a certain extent. What happens when your critical raw materials are used in small quantities and there's only a number of mines doing that supply? Do we have enough of a price increase to actually inspire that investment to take us through to new mine output? And what does it take to do that? So I've got comments down here. What effects do global politics have? I put that one in because, of course, we've had a lot in recent weeks about trade relations between the US and China. And what effect is that going to have? And we've got a very good example of exactly what can happen. So people, I'm guessing, will have been aware that there was a rare earth element supply crisis quite recently, where a political spat between China and Japan resulted in China withholding its rare earth elements from the global market for a while. There was a lot of political manoeuvrings on that, but there was also a lot of reporting about it. There was a lot of media. The prices shot up. The stock prices of the companies that were involved in exploration for rare earth elements went up. And so this is a very recent report by Cox and Kainicki just this year. And they actually charted 28 representative junior companies out of a total of about 400 junior exploration companies that were exploring for rare earth elements. And between 2006 and 2015, those 28 companies raised $6 billion of investment in that decade. And the majority of that within just 2 years. So that is an enormous investment. And after all of that investment, only 2 mines came online. So that is a very low return on total investment. And that makes a lot of investors very nervous of critical raw materials. And if you don't have investment, you don't have the capital to start up a nice new mine. So how do you address the problem? So this is an example of, the neodymium, the dysprosium, the rare earths that go into things like the wind turbine motors, but also the motors in your computers and things like that. Another example, a different group of elements, would be those that are used for doping the thin film cells that are on solar panels, so silicon panels that have just small quantities of these technology elements doped into them. And the issue with these is not that we necessarily need new deposits. Most of these elements, the indium, gallium, selenium, tellurium, germanium is in there as well, these are actually produced not by an isolated mine, extracting them just as a primary commodity. They're produced as byproducts of mining of things like copper, zinc, lead, and tin. They're produced as byproducts of the bulk raw materials, but they're only present in small quantities. So the demand for the bulk raw materials controls how much byproduct you can get your hands on. And so how do you then actually tackle that problem? Can you do it through geological research and exploration? And to a certain extent, there is potential for new types, innovative types of ore deposits. But the really interesting thing, it was a bit dark there, is that we can think about geometallurgical approaches where we take the whole system from our geological and mineralogical knowledge, and we take that information and we apply it to minerals processing, and we refine the techniques for how we suck out the byproduct metals from those bulk raw materials. And then we can actually think about that enhanced reclamation from manufacturing of electronics, but also processing wastes from mining. Now, indium's a really classic example. It's up there in that top right corner on the critical graph. The interesting thing about indium is actually there's quite a lot of it sloshing around geologically. It's there in the zinc deposits that formed at high temperatures. But not all of the zinc concentrates are diverted into the smelters that have a facility to extract indium. So the problem isn't necessarily a geological one. The problem is perhaps one of organisation. And so how do we address that? And that's where politics and regulation obviously does have a very large role to play. So what we'll have a look at next is some work that some engineering friends of mine did. This was written by David Leal Ayala. This one, it's 2014. The data are from 2010. It takes quite a long time to process the data. This is a Sankey diagram, a mass flow diagram that charts the whole system from extraction at the left-hand end of the Sankey diagram to utilization in the manufacturing industries at the right-hand end of the diagram. And the thickness of the line as a total is constant across the diagram, so that we have a large flow here, as in it's all coming out of mines as one type of material, and that equates to the addition of everything down here in all the end uses. And what these engineers from the University of Cambridge do is they look at the whole system and they find out where the biggest losses in the system are. And what we find here is there are some quite nice recycling loops that come around in here and take material back in. And the red lines are basically the waste stream and the processing losses. And what we can see as we go across this Sankey diagram is the red lines get thinner, which basically says that in the manufacturing engineering, the waste is relatively small. But over here, where we've got beneficiation losses to mining tailings, we've got huge waste at the mining end of the whole system. So that in a whole systems perspective, the biggest gains to be made on resource efficiency actually lie with geology and mining. Okay? And the engineers were quite surprised by this. And so there's an increased dialogue now about materials and manufacturers talking more to geologists and miners about how to address this. So, what else can we say is a challenge that we face? We'll call it a challenge rather than a problem. The other challenge that we have in Europe is that we have this great manufacturing sector, but we don't have a great raw materials supply sector. And what we do know is that in the past we did. So what has happened in Europe is that we can say, well, the world-class deposits, as they were described when they were being worked, have either been mined out in Europe or simply can't compete with the global world-class deposits, unless they exist at greater depth under Europe. So either we have to find new types of deposit locally, or we have to look deeper. And then we have the other problem that if we have new types of deposits, the ways that mining is set up might not be ideally supporting those new types of deposits. And why is that? Well, the global mining giants have a lot of overheads. They're very, very large companies that ship globally. They have to work on public markets, proving the viability and the longevity of their mines. And in order to do that, and for investors to have certainty that they may have a return on investment, there are a lot of codes that have to be adhered to prove geological viability. And only then is a big mining company going to raise the billions of dollars it takes to actually start up a mine. And so that means mines have to be big. So this scheme of proving geological certainty through extensive exploration and sampling campaigns isn't really fit for purpose for critical raw materials in small complex deposits. So maybe we need new types of deposits, but maybe we just need new ways to mine. So the geological opportunities, this is a very simplistic view of it, that exist in Europe. We know that we produce very little of our critical raw materials. We also know that Europe was historically a powerhouse of raw materials production. And we do still have some good mining in Europe. Those mines that we have, particularly down in Cornwall, where I've come from today, are not exhausted. Some of them are economic now. But when we say they're economic, we mean that if we can get them up and running, they will turn a profit. But we still need the money to get them up and running. So a lot of the reasons that our UK and European mines have closed is that other bigger mines opened and undercut them price-wise, or there were legal and land disputes that closed them down. And those bigger mines that reduced the price and made these uneconomic, they're getting worked out. So the system is coming full circle. And now it's about how we actually raise the money to get it kick-started again and how we do it right. So what we've got is we've got the historic mines that are not exhausted. We also know, this is quite an interesting thing, that our historic mining legacy was focused on things like copper and tin and lead. It wasn't focused on indium and tellurium, selenium, or in Cornwall, antimony, to a certain extent, bismuth, to a certain extent, tungsten. These things were thrown away. So they already exist in tailings and mine wastes in Europe. And those things are certainly being looked at. And then, of course, we have the hidden deposits. If we know we had them historically at surface level, can we now, with our improved exploration and mining technologies, follow them deeper underground, where we will actually have less surface impact than in previous cycles of mining in Europe? And then, of course, we need to think about the active mining districts that we do have and how we increase byproduct potential. So this is just a little example here of a map of rare earth deposits globally. And a lot of this work, well, nearly all of this work, is actually done by the British Geological Survey under NERC here. And essentially what this is showing, obviously you can't read all of these, but these dots here are showing, the big blue and the big red dots, that the biggest and most dispersed supplies of rare earth elements are found in carbonatites and alkaline rocks. So, straight off, we can see that although China produces most of the world's rare earth elements, the rare earth elements are actually distributed fairly evenly around the globe. So geological availability is not the issue. Right. And the other thing we can say, this is a graph of grade against tonnage, showing that Bayonobo is the only rare earth element deposit that actually qualifies as a giant ore deposit. The rest are much smaller. There's an emphasis on these bigger deposits here to higher grade at greater age of deposit formation. And it's a function of repeated processes, geological processes, taking the geological system through iterative stages of concentration of rare earth elements. So the mobility of rare earth elements in the geological system allows them to be concentrated again and again and again until they get to high grade. So we can take those basic principles and we can say, okay, what shall we do to try and improve how we find deposits? So I'm going to show just two case studies. Case study one is of a regional survey that was done to improve exploration for all raw materials. And case study two, a research program to try and look deeper beneath Europe. So I like this photograph. It shows, as opposed to all the photographs that geologists often put up of a beautiful sunshine type environment where they do their nicest field work, this is what all my field work in the Mourne Mountains looked like. Okay, this river is actually a footpath. What were we doing there? Well, we were in the Mourne Mountains, myself and a colleague from the University of Brighton and the British Geological Survey, following some clues given to us by the TELUS exploration programme. That one was based in Northern Ireland. It's been extended across the border into Southern Ireland, and it's been extended into the southwest of England as well. And the TELUS survey is basically a regional, European and national funded survey that flies geophysics, does soil and bedrock sampling. It even samples moss and biological materials at great intensity, and stream sediment samples as well. And so we were looking at the Mourne Mountains, which had previously been explored for a number of commodities, with a series of granites in this case, slightly subalkaline in composition. And what were we looking at? This is the general context of the known geology. But what the TELUS programme provided us with was shallow and deep soil samples. These were the bits we were using and interested in particularly. Shallow and deep soil samples on a 1 kilometre spacing over the whole area. And while the shallow soil sample might record anthropogenic activity, the deep soil sample is strongly influenced in its chemistry by the rock that underlies that soil. And so we can use that as an exploration tool. What we did, we've got the soil, deep soil niobium concentration in the triangles here as spots over this granite outline here. And so we see that these are the largest concentrations of niobium in the deep soil, which are across these roof zone granites here. When we looked at the heavy mineral concentrates of the dense minerals that were separated out of stream sediment, we find that the niobium-bearing mineral is most common where we get these big spots over here. So the niobium-bearing mineralization that we understood would be creating niobium anomalies when we entered this field area has a completely different distribution to the soil sample. So it says that we've actually got to rethink how we do things a little bit. So what we did is we followed the niobium anomalies in the deep soil and we sampled some bedrock and we tried to find out which minerals were actually creating the enrichments of both rare earth elements and niobium and some other materials as well. And so we found these niobium-bearing minerals, no problem, but fergusonite was fairly minor. And on the basis of all of this work, we produced a petrogenetic scheme, which was very nice and taught us that, yes, where we found the enrichments, we were seeing these repeated schemes of concentration, where it starts with fractionation. And then we have metasomatism, fluid migration, and then further migration from groundwaters along fault systems and things like that. So that fits very nicely. But the takeaway message was that in our short geological research project, which was a very short turnaround one, the survey results indicated there was more going on than we actually found. And what we don't know is if the soil and the stream record were telling us about rocks that had been eroded away, or they were simply telling us about things that existed that we hadn't found because they were undercover. And they had been at one point eroded and then covered with soil subsequently. So that basically says, right, we need to use more methods again. So for the rare earth elements, there's this big project here, which is actually led by Francis Wall of the Camborne School of Mines. And it's developing new geomodels to explore deeper for high-tech critical raw materials in alkaline rocks and carbonatites. There has never been such a big project on carbonatites and alkaline rocks as this. This model is the only real model that exists for how carbonatites and alkaline rocks work. And it dates from 1977. It's a brilliant, brilliant piece of work, particularly given that it wasn't fully proven that carbonatites were magmatic rocks until 1962 when Eldonia Lengai erupted. So a phenomenal piece of work on the back of a lot of researchers, particularly Michael Labat, who drew it, but basically the geologists who worked for the geological surveys in the east of Africa for many decades. And what we now know, particularly since there's been increased access to Russian deposits, since we've been finding a lot more European deposits, we know that the geological case studies that were used to build this model do not provide the whole story. So this model has satisfied more or less what we needed for 40 years. But in the current climate of securing supplies of critical raw materials, we now need the new geomodel, which will take us forward for the next 40 years. And so what we're doing, we've got just a couple of classic pictures here. There's Aldonia Lengai, not erupting at the present time. A volcanic edifice. And here's Napak, where the nephelonites are in the background, and we've got this little carbonatite core in the center, showing that what we see at the surface of a volcano doesn't necessarily reflect what's at depth. And so the idea is that if we can find the right natural laboratories that give us these erosive slices through a model, we can try and reconstruct much better what that looks like. If we can do that, and we can then correlate those slices with very strongly refined geophysics and downhole testing, then we might actually be able to translate from that three-dimensional geomodel into exploration tools. And there's another case study we're using here. I've put this one in because Holly Elliott has published this just this February. This is the first of her papers. Recognizing that there is a zone of phenetization where fluids emanate from the igneous rocks and transport some critical metals into the rocks that overlie the interesting stuff. The question becomes, can we use the mineralogy in phenites to tell us what rocks lie at depth? So it doesn't just have to be about geophysics and drill core and downhole testing. We can actually use the mineralogy in geological case studies to suggest what might be prospective and what might not. We might save ourselves a lot of expense in drill programs if we can rule out a lot of carbonatites and alkaline rocks. And so that's Holly's task. But what she's produced in the first instance is, as I say, this field of research, particularly compared to granites and other areas of geology, is really quite young and new. And so there was no real consensus on how phenites would form, what was their depth control, what mineralogy is there consistently, and how do we actually define the terminology that we used? And so that's what's been produced this year. And so Holly has developed schemes and looked at a lot of different deposits, a lot of different phenites, and produced these beautiful cathodoluminescence images to try and constrain the framework to start to do this. So it's very nice. And then the other thing that we do when looking at these case study areas is we actually go and visit some of these very alternative deposits. Everyone's standing around looking puzzled for a very good reason. It's a very, very puzzling deposit, this one. This is the Pianciano carbothermal fluorite deposit. And basically, there's still geological research going on about how this actually forms, but there are byproduct rare earth elements in it. So that's very nice, and we're moving forwards on that. But let's just say we can find these things. Now, this one's a big mine. This is Mount Weld, a rare earth element mine in Australia. But we know that extraction from these large deposits requires big feasibility studies to show long-term viability. They need a lot of infrastructure. We know that there can be a poor return on investment. And then it can be very difficult for small companies to carry on trading. So of those 400 companies, a lot of them went out of business. And that concentrates production further. And so this is really the nub of the problem as well, is that we can find things. We know we can. We can do the geological research to find new ways to find things. But once we've got them, how do we actually make it economically competitive to get them out of the ground? So that's what the Impact Project is about. It works on the basis that if we know the geology well enough, and there is a fluctuation in demand or supply for a variety of reasons, how do we actually kickstart mining at known deposits? So we're recognizing that there are a lot of deposits available, and they are not necessarily adaptable and responsive to market conditions, and that's what we've got to do. We need to better balance supply and demand, and we need to be fairly nimble about how we do it. So a business has to be able to move from extracting one commodity in one place to another if it's going to switch on mining in response to demand. In order to do that, we've got to reduce CapEx, the amount of investment needed for capital startup of mines. We've got to take some of that cost and put it into operating cost, OPEX. We can do that if we reduce the amount of rock that is extracted and we reduce the amount of energy. But in doing so and tapping smaller deposits, the life of mine could be a lot shorter. So there are challenges inherent with the whole ideology. And essentially, what it boils down to is this supply-demand imbalance is not just a geological one. It's a business problem, a technological problem, a societal problem, and a regulation problem. So we're starting by looking at well-understood ore deposits and how we make those responsive. So we're doing that in the context of critical raw materials in bulk raw materials. We're looking at lead deposits and subsequently then at antimony deposits in the West Balkans. And this is the Olivo mine here where we will be deploying a test extraction plant this summer. And so geological uncertainty is a real issue, and geological variability in these small complex deposits is a real issue. How is this variability, even across a transect in the mine, actually going to change the behavior of materials, the hardness, the friability, the density of materials that enter a processing plant? And so we have to develop geometallurgical approaches. We then need to think about how we selectively mine these materials. So can we develop a new mining tool that's smaller in size, that takes out less rock, loops some rock in a backfill solution straight back into the system, and how that actually reduces the amount of energy-intensive crushing and grinding that's required. And so those things are all happening, but not in isolation from this one, is that we need to ensure that if we are going to mine anywhere, not just close to home, we do it responsibly. In my humble opinion, I think if we want to mine right, we should do it in our backyard, where we have good environmental regulation, where we can keep an eye on it, where we can make sure it's done right. It doesn't always go down very well with a lot of people, that opinion. But nevertheless, that's what I feel. If we want to do it right, we don't push it into other countries. And this is obviously a very multidisciplinary consortium project that tackles a lot of things. We've actually got a conference coming up in May in Aachen, if anyone wants to look at the website and see what that's about. And this is the beautiful landscape in Bosnia where this mine is located and where there's a very, very good relationship between the mine and the community. But my last few slides are about the ethics of mining. I've already said I have quite a strong opinion about environmental regulation and doing mining right. But it goes above and beyond with small-scale, complex mines. If they're small-scale, whether or not we can get them kick-started quickly, the life of mine is going to be short. And so the benefit to a community might also be quite short-lived. So there is a real chance that our transition from a pre-mining to a post-mining community will be accelerated. And so there is a dialogue needed to think about what is to the good of a community. So this is actually something I'm doing quite close to home, in Ireland, in Cornwall, and in Iberia as well. But in Cornwall, we've got a very good relationship with the Perranzablou community and museum. If anyone's ever been to Perranporth on holiday, they might know exactly this beach. And essentially, this is a post-mining community that is very concerned with its industrial and its cultural heritage and how it uses that to promote and create sustainability in its community. And if we can understand the identity and the path dependency of post-industrial communities, we can actually think about how we build that into our social license to operate. So, my summary, I'm running slightly over time, but we'll get there, is that the geological side of it is very important. The raw materials, it's about the small quantities used, the investment problems, as well as the technical problems and the regulation problems. We need to safeguard against reducing the number of smaller operators. We need to support smaller and medium enterprises for a healthy security of supply. We need to geologically and in terms of engineering identify the intervention points for technological innovation. And we have to think very carefully about the societal challenges that critical raw materials will create that are different to those of the big bulk raw materials. And so my final comment, I can let you read that, is that yes, we need to continue to work in our traditional role as geologists, but we need to think increasingly about how our discipline interacts with other disciplines and to create the dialogues with miners, with minerals processors, with engineers, with manufacturers, and with environmental agencies and communities. And so it's that cross-sector dialogue that I see in my personal experience as my greatest way to make a step forward change in securing supply of critical raw materials. And finally, just to prove that we do still get to rather far-flung places, this was a trip in the autumn to the southern Gobi Desert in Mongolia to look at the shallow plumbing system of a carbonatite fluorite deposit. And I will be glad to take any questions.
Brilliant, thank you very much, Kate. Does anyone have any questions? Because I have lots. There we go, gentleman at the back.
This question doesn't refer to our backyard, but can you say something about the potential for mining on the seabed?
Yes, I'm a little bit opinionated about that as well. So mining on the seabed has been proven through a couple of big EU projects, actually, to be technologically possible. And the argument is that it is environmentally beneficial and of lower impact than mining on land. I have not seen the proof that that is the case. I understand that the technology works on the basis that essentially it's hoovering up and sorting material and putting it straight back down. And so the big problems that we've had in, let's say, bulk aggregate extraction in offshore regions, which has changed longshore drift and increased erosion of coastal areas because of the removal of bulk materials, that would not happen in the seafloor mining context here because the material is returned again. Now, where it's been investigated actually in Cornwall, it's not got going because, of course, there are eel spawning grounds that have to be protected. And so obviously with the glacially lowered sea level and all the industrial activity, there's been a lot of runoff of tin to Falmouth Bay and other areas like that. And so they're working very hard on the environmental protection in those kind of research projects. But for the deep sea mining for manganese nodules, where there is a proven critical raw material concentration, it's technologically feasible. It's expensive at the present time. It is cited as being environmentally beneficial. My problem is that I think the sites would need to be located away from deep sea currents. I would not like to see increased anoxia in deep sea currents where they might then affect upwelling areas which are quite sensitive. And I don't believe the research has yet been done on that. So as long as nobody grants permission to do the licensing until that's ironed out, fine. So the result is, I think there's a long way to go in terms of environmental regulation before it should be done. We know that a license has been granted in Papua New Guinea, but that does not mean that mining will commence there. So it hasn't, although the exploration license is there, they haven't actually got the planning permission from the local communities to do it yet. And that one is actually relatively near shore, and it is close to fishing grounds, and so it is sensitive. To my mind, again, I would think if we recognise that the ocean is actually where our greatest biomass is, and the global ramifications of starting large-scale offshore mining could be large, I think we should stick to what we know to begin with. A personal view, yes.
There's a microphone just coming.
Thank you. Yeah, great talk. How much work has been done on analysing the tailings of the very old mines in the UK? And there's quite a few of them. What
Yes.
comes to mind are mines like Anglesey. There was a large copper mine there, and
Yes.
so on.
So you're talking about Paris Mountain.
Yeah.
So there has been a bit of work done on that one, and yes, they are there. It's very variable, and the technologies to extract metals from tailings exist and are already used in various parts of Africa for extraction of gold from previous mine wastes. So there is technology available there. The problem is in the business model to actually do that is how many mines do you need to be able to access the tailings of to make it economically viable? If we compare Paris Mountain to Cornwall, they're two very different animals because Paris Mountain, you can still see the impact of mining, you can still see the coloration, everything like that. In Cornwall, where you've got legacy deposits, we've got legacy mines, they're pretty much cordoned off. And the remarkable thing is it can be very difficult to actually obtain samples of waste in Cornwall because the mineral collectors pick them over very thoroughly. We've actually, with a PhD student, we've spent quite some time trying to do that. It's quite a challenge in some places. So the contamination might not be as bad on land as we think. The main problem in Cornwall is fallout from historic smelters, which gets into the soil. and that isn't then concentrated in an area that you could actually tap it. It's actually dispersed fallout in agricultural soils and things like that, which is again something that is being looked at for obvious reasons. Yeah.
Is there one last question? Yes, here we go.
Thank you. When you're talking about shorter term mine life and the effect on the communities, how long are we talking?
So it can be anywhere from 6 months to 10 years. But normally, you know, a big mine, you're talking about generations of employment. And what we're talking about here is not even one generation of employment. So a big plug for the company that I'm working with in the West Balkans. This is a company, Minico. And there's actually a company that do this in Namibia as well, B2 Gold. What they're doing very well is they're thinking about what businesses they seed that the mining can be used to kickstart for the post-mining era. It's very important in Bosnia as well. What they've been doing is they've been bringing geologists back into the post-conflict area who were part of the Bosnian diaspora before and during the conflict. So they're actually bringing geological and mining technology in Bosnians back from Australia, Uzbekistan, Russia, even the youth group who had moved out of the Olivo municipality into Sarajevo and places like that. They're employing local people to be able to move back to rejoin their families. They've also, because they have a post-Soviet mine that the war rolled over, the tailings were destroyed, the environmental devastation was quite large. The first thing that the mine have done is tidy all of that up. So even with a short-ish, in fact that one's going to last probably a couple of decades, it's going to be a good one, but even with a shortish life of mine, the benefit to the community is there at the outset. And so often with social acceptance to mines, there will be a lot of enthusiasm early on when a community might think they're going to have a lot of gain, and then there will be a big dip in social acceptance of a mine as they realise that it's not all rosy. But in effect, with this particular mine, the benefits are immediate to the community. Yeah.
Fantastic. We've just sneaked past 4 o'clock, so I'm afraid that's it for this afternoon. But there will be a repeat, of course, this evening, and it's all been recorded as well. So thank you very, very much, everybody. Thank you, Kate. That was fantastic. Round of applause.